All right, I had these all recorded for automotive, but I know when I did them for automotive, I used some automotive specific examples. So I'm re-recording for you folks. So if I miss something or if I stumble over my words, it's probably just because I've said this 2 or 3 times recently. So we're going to look at parallel circuits in this section. So parallel circuits are circuits that have multiple paths for electrical current to flow. Multiple paths is really, really, really important. Okay, this multiple paths is what makes a parallel circuit. All right, so when we have multiple paths, so the current flows from the battery, but the current can split up through those paths. Now, how much current goes in each? Is it going to be the same or is it going to be different? Well, I like to visualize that as a kid at the beach. I'm sure you guys have all done this. I wasn't much of a swimmer. Maybe I just spent too much time digging in the sand on the beach, but you're playing on the beach, you dig your hole at the top, and then you dig these little channels that go down towards the water. You've got one that's a wide one that allows lots of flow and a skinny one that allows a little flow. You fill up your reservoir and you watch how quickly it empties. Where's most of the water going to go? Most of the water is going to go down your wide channel because it has less resistance. Well, Kirchhoff's law with current works the same way. The most current is going to go through whichever of these light bulbs has the least resistance. The least current will go through the light bulb that has the most resistance. Okay, so the current could be different in each branch, but it's going to add up to be whatever is coming from the battery. So Kirchhoff's law says that the total current at the source has to be equal to the current through branch 1, branch 2, and branch 3. So here we have branch 1, branch 2, and branch 3. Voltage, on the other hand, is the same through all of them. And that's because the push from the battery is the same through each branch. Okay, so we could, let's say we disconnect this branch and we disconnect this branch. There's still just as much push leaving that battery. Okay, so that's why voltage happens to be the same. It's also why when you're measuring voltage, you'll notice you measure across a component. One lead on one side, one lead on the other side. And that's because voltage is the same when it's done and measured in parallel. If you measure voltage in series, by breaking the circuit and adding your voltmeter in, that's not going to work, but that will work if you want to measure current, because in series, current is the same. I'll let you think about that one. So voltage is the same throughout a parallel circuit. So the push is the same through each branch. And then resistance uses a really crazy formula. Resistance is how much the current is slowed. So how much the current is slowed from the battery is actually less than the resistance through each of the branches. And that's because charge is coming out and it's feeding 3 branches, which means from the battery's perspective, there's less resistance because there's more places for that current to go. So you're always going to get an equivalent resistance that is smaller than the individual resistances of each of the resistors in the circuit. So let's do a couple calculations. The calculation for resistance, I'm going to use fraction method first, and then I'm going to give you a calculator shortcut because sometimes that calculator shortcut can be quite handy. But knowing how to use fractions is great when the numbers are easy, which you will have for the most part. All right, we want to find, first of all, the equivalent resistance, and then I'm going to build the chart. Actually, we might as well build the chart now. So we need to find current. So we need resistance, current, current through each branch. Current drawn by the battery. I wanted voltage. Current through each branch. Yeah, we'll leave that. We'll leave the wording the same. There we go. Current through each branch, current drawn from the battery, and total power dissipated. So we're going to need E, I, R, and P. Maybe this is the way to do it, is to my headings first. And then we have R1, R2, R3, and our source. All right, so let's fill in what we know. So we know we have 90 ohms, 90, 45, 180. Our total we can't calculate because we can't add them easy. We're going to have to follow a formula, but we know we have 9 volts at the source. I want to calculate the equivalent resistance, and we're going to calculate it first using our formula just so you get used to it. There is a way to get around calculating it this way, but I really want you to use the formula. So Kirchhoff's law says that 1 over the equivalent resistance, so this is like the total resistance seen by the battery, or the equivalent resistance to all these resistors together as far as the battery is concerned, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so we plug in our values. 1 over REQ, hopefully I have enough space, is going to be equal to 1 over 90 plus 1 over 45 plus 1 over 180. You guys remember fractions, hopefully. Make common denominators. 1 over 90, 180 is our common denominator, 2 times 90, so we're going to have 2 over 90, plus 45 times 4 is 180, so we're going to have 4 over, 180, plus 1 over 180. So 1 over REQ is equal to 2 plus 4 plus 1 is 7 over 180. REQ, we flip, in order to find the equivalent resistance, we flip this side and we flip this side. It's equal to 180 over 7, which is equal to 25.7 ohms. So it's a lot less than each of the others. And that's because there's more places for the current to flow. The current can flow through this branch, and this branch. So it gives it appears like there's less resistance in the circuit. This allows us to calculate how much current is coming from the battery. Current from the battery is just going to be equal to 9 over 25.7, which is equal to 0.35. It's 0.35 amps. Now, we said earlier that the voltage push in parallel, the voltage push from the battery is the same as the voltage push from R1, R2, and R3. So we can fill those in. Current, 9 divided by 90, 0.1. 9 divided by 45 gives us 0.2. And 9 divided by 180 gives us 0.05, 0.1, 0.2, and 0.05. All three of them add up to 0.35. That means we calculated our resistance correctly. So the resistance is the one that's tricky to calculate in parallel. That's the hard one. The rest of it's easy. Power uses the same formula. So we're going to do E times I. 9 times 0.1 gives me 0.9. 9 times 0.2 gives me 1.8. 9 times 0.05 gives me 0.45. And 9 times 0.35 gives me 3.15 watts. 0.9 plus 1.8 plus 0.45 equals 3.15. Power adds, that's too many S's, not enough D's. Power adds in series and parallel. It's the only thing that's always the same in a circuit. Power always adds up, no matter what your circuit looks like. If you can calculate the power the power that's required for each component will always be equal to the power that's drawn from the source. Okay? So power always adds up. One of those things that's always the same in a circuit. We won't do a lot of calculating with power, but it is one of those useful pieces to have. Now this is another one that I'm going to do without using the chart. I'm going to use it and I'm going to do the same thing as I did before and just label at each spot because that's probably my favorite method rather than using the chart. The chart is good in some circumstances, depends on exactly what you need to find. So here we want to find the missing values. So in order to find the missing values, we need to figure out one more piece of information for all of these. Now, current is different at the battery than it is through each of the sources. We can't use current to put it all the way through. If we knew voltage, we could put voltage everywhere, but we don't know it. But we do know the three resistors, so we can find out the voltage at the source. If we can find out the equivalent, I said voltage, the resistance at the source. If we can find out the equivalent resistance at the source, we can calculate the voltage at the source and the problem is basically solved. So in order to figure this out, the equivalent resistance is going to be equal to 1 over 30 plus 1 over 30 plus 1 over 30. No hard fraction math here. Add the numerators together. 1 over equivalent resistance is equal to 3 over 30. So equivalent resistance is equal to 30 over 3, which is equal to 10 ohms. Well, if you think about it, the battery is pushing current and it's got 10 amps of current to split between 3 branches. Does it make sense that the battery, from the battery's perspective, it would see a third of the resistance? To me, it does, because 1/3 of the current can go here, 1/3 of the current can go here, and 1/3 of the current can go there. So from the battery's perspective, it's able to split that current up. I don't know if that made the explanation any easier, but sometimes it's hard to explain things that are logical to a person. If we want to know voltage, voltage is going to be equal to current times resistance. So 10 times 10 gives me 100 volts. Voltage is the same everywhere. Since voltage is the same everywhere, 100 divided by 30 gives me current, which is 3.3 amps everywhere. Because each resistor happens to be the same. And it's only because each resistor happens to be the same. One final example before I show you the calculator method instead of fractions. We want to know the missing values in this circuit. You just have two pieces. So let's find our, again, same process. We'll find our resistance, RT. I really want you to find that first, only because I want you to practice it. Now, you could argue with me that you don't have to, and that would be fair, and we'll look at that version too, but I just want you to practice it. So equivalent resistance, 1 over Req equals 1 over 4 plus 1 over 3. Common denominator is 12. 3 over 12 equals 4, whoops, plus 4 over 12. That should be a plus, not a, okay. 1 over Req is equal to 7 over 12. So Req equals 12 over 7, which is equal to 1.7 ohms. Now you could have said, wait a second, you didn't have to do it that way. And you're right, I don't have to do it that way. I could have started out and said, well, I know the voltage at the start, and I could just put 12 here and 12 here, which is fair. And if we know it's 12 volts here and 4 ohms is for resistance, I is equal to voltage divided by resistance. So 12 divided by 4 leaves me with 3 amps. And over here, 12 divided by 3 gives me 4 amps. I already told you that current has to add up. 3 plus 4 gives me 7. 12 divided by 7 equals 1.7. So that's a way to practice your equivalent resistance, and then you can actually use your math to double check it. All right. Adding parallel circuits is probably one of the most challenging pieces of the electrical math. The rest of it's all easy stuff, just using E equals IR for the most part. All right, calculator method to find equivalent resistance. Your calculator has some tools that can help you out. Now, this is the calculator that you would see on your block exam. You will see this button here. It has this 1 over X. It's the same as saying X to the minus 1, okay? These are the same thing. So for others of you, you may have a button that says x minus 1. Look for that on your calculator. I want you to try do it on the calculator because it's actually really easy to do. It's not complicated at all. All right, so this button that I have circled will do this math, okay? This -1 math that we see here. You have to press shift first, and then press that button. All right, so this is 1 and this is 2. All right, so you're going to enter your number first, then you're going to press shift and that 1 over x button. If your calculator, my other calculator, has a button that just says x minus 1, I don't have to press shift, I can just use that button. So how do we find equivalent resistance? Well, I've got it written a bunch of different ways. I said, well, okay, if 1 over r is the same as r minus 1, we could write the formula like this. And your ILM, if you want to go to the library and look up your ILM that's just used for studying block exams, you will see equivalent resistance written out like this. And then what they'll say is, but that means equivalent resistance is really equal to this. You notice here it says REQ instead of this -1, and we got rid of the fraction. And that's because we put this -1 over here. What that -1 does, it says take the number and flip it upside down, just like we took the fraction, flipped it upside down before. So to put this in your calculator, you do the first resistance, you press the -1 button. Type in the second resistance, press the -1 button. Plus the third resistance, press the -1 button. Then you're going to press equals. And then you're going to press the -1 button again. Okay, I'm going to walk you through the steps on one, and I would have been smart if I had my calculator right beside me. I'm going to grab my calculator and we'll walk through the steps on one just so that you see, you can put it in your calculator to figure out. This is really convenient if you can't get a common denominator. Now, the example that I give you on the next slide, you could get a common denominator for. So if you want to test both methods, you're welcome to it. But this method is really convenient when you don't have a common denominator, if you have weird decimals, something like that. All right. All right, I've got my calculator. So I want you to use the equation that I just gave you using your calculator to calculate the equivalent resistance of 3 resistors measuring 15 ohms, 30 ohms, and 50 ohms, all connected in parallel. So we'll show you how to type that into your calculator. In your calculator, you're going to start, you can use brackets if you have a calculator that you know how to use the brackets on, but if not, we're just going to use our equals button. So what we're going to do, I'll give you the number sequence. You're going to type in 15, and then you may have to use shift. Then you're going to find your x minus 1 button or the 1 over x button. One of those two. Okay. Then you're going to hit plus. Then you're going to do 30 and the same thing. The 1 over x button. Plus 50 and the 1 over x button. Then you're going to hit equals. Okay, so and I'm going to give you the decimal that you're going to get just so that you know if you've got it. So okay, hopefully you have the same decimal I have. I get 0.12. Then you're going to press so you get 0.12 is on your calculator. Then you're going to press that 1 over x button again, or the shift 1 over x, and you will get a resistance that is equal to 8.33. Let me erase what I didn't mean to write there. You get 8.33 ohms. Okay, let's check it the other way. Well, our other math said 1 over REQ was equal to 1 over 15 plus 1 over 30 plus 1 over 50. Well, the common denominator is 150, so we would have 10 over 15 plus 30 times 5 is 150, so 5 over 150 plus 3 times 50 gives me 150. Adding those together, we get 18 over 150. Okay, that's 1 over REQ. So REQ is equal to that number flipped. So 150 divided by 18. And we get 8.33 again, because second guessing there for a sec, because I'm like, how in the world did I get 10? I typed in 180 instead of 150. So we get 8.33. So both of them work the same way. You can use whichever method you want. There will be times when using the calculator will be to your advantage. Not so much for a lot of the questions I'll give you, but it is good to know how to do that. That's much faster to do than it is to type 1 divided by 50 plus 1 divided by 30. 30 plus 1 divided by 15. So knowing how to use some of those buttons on the calculator that you don't use every day can be really useful. And that's all that we have for parallel resistors. So that has you all up to that section. The next thing we're going to have you do is I'm going to have you do a little simulation lab, and I'm going to get you to look at combination circuits. We'll cover combination circuits, transformers, and then it's going to be February break.